This is Lecture 1D for Calculus 1 on exponents and logarithms. Previously we were looking at the power function. In the power function, the variable is in the base of the exponent. For exponential functions, the situation is reversed, and now the variable is up in the exponent. We're going to look at the graphs of exponential functions as a family of functions, just as we did for the power function, but we're going to separate them into the growth equations, where f of x equals b to the x, b being greater than 1, and decay equations, f of x equals b to the negative x. You'll notice on these graphs that all the exponentials go through the point x equals 0, y equals 1. Here's some graphs of growth equations. This is 2 to the x in red, 3 to the x in blue, and 6 to the x in green. Notice the order of the curves. 6 to the x is greater than 3 to the x is greater than 2 to the x when they're in the growth phase, like this. When you're over here in this decay region, 2 to the x is greater than 3 to the x, which is greater than 6 to the x. In other words, the bigger the base, the faster it grows and the faster it decays. And the difference between this growth and decay is right here at the point x equals 0, y equals 1. Now here are the decaying exponentials as a family of curves. By graphing them like this, you can see the change again with the base. Of course, this is the same as that previous equation, or the previous graph, just with the curves rotated about the y-axis. When you replace x by minus x, you rotate a graph about the y-axis. Here's 2 to the x again in red, or 2 to the minus x rather. Here's 3 to the minus x in blue, and the 6 to the x is in green. Now, what is the domain of the exponential functions? The domain is all the real numbers. This was established in algebra. And the range, of course, is all the y's that you get from this function. And as you notice here, the function never gets to 0, and it never goes negative. So the range is all y's strictly greater than 0. Now, I want to talk a little bit about what's meant by exponential growth. You hear that mentioned a lot in the newspaper or in casual conversation, and it's usually taken to mean a very rapid growth. But there is an actual meaning to exponential growth. It means that the rate of growth is proportional to size. The bigger it is, the faster it's getting bigger. So that's what exponential growth really means. And exponential growth is truly very rapid. In fact, exponential growth is faster than any polynomial growth. This was the basis of the Malthusian catastrophe. Thomas Malthus observed at that time that the population seemed to be growing exponentially, but that agriculture was only growing linearly. And since an exponential outgrows any polynomial, it certainly would outgrow any linear function, which is just a polynomial of degree 1. Then when the population caught up with the agriculture, there would be famine, starvation, there would be catastrophe, all kind of misery. And then the situation would get back under control. This hasn't happened. The reason is that populations do not consistently grow exponentially. Some countries right now, Germany and Russia, have negative population growth, so in a sense you could say they're decaying exponentially. And agriculture has not grown linearly. In fact, it's grown a lot faster due to technology. In exponentials, we have many exponentials with a base of e being this irrational number starting off 2.71828. It is an irrational number just like pi is an irrational number. However, to understand pi is very easy. Pi has a geometric basis. If you take the circumference of any circle and you divide by the diameter, or twice the radius, that ratio equals pi. It doesn't matter what circle it is, whether it's a great big circle in a crop field or a little tiny circle on the end of an eraser. The circumference divided by the diameter equals pi. For e, there is no geometric way to understand it. In the written lecture that accompanies these audio files, I derived e from compound interest, as the frequency of compounding goes from a discrete number such as semi-annually or quarterly, monthly, daily, hourly, till that becomes continuous. When it becomes continuous And if you work through that derivation, you will see with the change of variable you get this expression, 1 plus 1 over n raised to the nth power. And as n gets bigger and bigger and bigger, n is related to the number of times per year that the interest is compounded. So as that number of times approaches infinity, that means it would be compounded continuously. The value of this expression approaches 2.71828. That's not a very easy to remember geometric definition, but that's one way to derive E. There's another one to calculate E, and that is as a result of this infinite series, 1 over k factorial, k going from 0 to infinity. On one of the homework problems, I think I asked that you just estimate in the exponential for E for some growth or decay equations. So I'm going to go back to those slides and show you where E goes now. Here is that collection of the family of curves for the exponential growth equations. You can see how they're ordered: 2 to the x, 3 to the x, 6 to the x. Because E is 2.718, it is between 2 and 3, but a little closer to 3. And I have put in here in a dashed line the graph of e to the x. So when it's in a growth equation, it's a little bit less than 3, but greater than 2. And when you're over here in the decay, over in this region, then the ordering is 2 to the x, then e to the x, and then 3 to the x. So it grows faster than 2 and decays faster than 3 to the x. In the graphs that we just saw, there was no end to the growth. If you use that to represent a population, it would just keep growing. The bigger the population got, the faster it would be growing, and there would be no end to the growth. That is not very realistic. So the exponent itself, just by itself, will predict a very unrealistic growth, an never-ending, always getting bigger situation. However, it can be used, in fact it is a basis of equations for limited growth that are much more realistic. When you look at these equations, they might at first look very complicated, but when we study them, the first thing to do, and this is true for any function, is look at its extreme value. Always look at what does it do at 0. Put in the value of 0 for the independent variable. Put in x equals 0, t equals 0, whatever the variable is you're working with, and see how does it behave at the start. Then look at what it does as t or x becomes very, very large. This is how you look at a function in terms of its extreme values. In math, this is the equivalent of the engineering sketch. And engineers also always look at the extreme value of any function. Is it correct at 0? Does it behave correctly at the start? Will it predict realistic values with the extreme values of the independent variable? Here's the first equation of unlimited growth. I'm calling it the creep function. There's also creep is a feature in mechanical engineering and in strength of materials. It's a little more complicated than this, but you get the same idea here, and you'll see in a few minutes why this is called the creep function. So the function itself is a, it's a function of time, equals some constant, a max, which gives a hint on the purpose of that constant, times, and then in parentheses you have this exponential 1 minus e to the minus kt. We're going to let k be positive, and right now let t be greater than or equal to 0. Okay, looking at the extreme values, we want to know what happens when t is 0. So we substitute that into the equation, and we find that we get the term in the exponential of e to the minus 0, get that evened out, which is 1. So in parentheses, you have 1 minus 1, the answer is 0. This curve starts out when t equals 0, its value is 0. Now look what happens as t gets very, very large, and we say as t approaches infinity, since it can never get there. As t approaches infinity, this decaying exponential approaches 0. Okay. When it approaches 0, it is essentially not in this equation, so I'm going to draw an x through it in a minute. So I'll just x it out, and you're left with a equals a max times 1. So in the limit, as t becomes very, very large, the exponential goes away and a approaches a max. It starts at 0, it goes towards a max. Because of that nice smooth behavior of the exponential, it approaches it very smoothly. And here's a plot of a particular creep function where I've set the max, a max, to 1 and the k to 1, so we can see its behavior. It starts here at 0 and it creeps up here until as it approaches asymptotically to the line a equals 1. And that's the behavior we deduced algebraically on the previous slide. Note the very smooth decay of e to the minus t, and that's reflected in that smooth increase in the creep function as it approaches its asymptotic value. Now we'll look at another equation of limited growth that's a little more complicated than this one, but the curve mirrors reality a little bit better. This is the logistics equation. The logistics equation itself could have many more terms. This is a rather simple version of it, but it's enough for us to start understanding it. Again, I've made the restriction that k be greater than 0, so the exponential is, it's decaying for t greater than 0, it's a growth for t less than 0. So again, we look at where does this equation start. We set t equal to 0, same scenario here. We have e to the minus 0, which is equivalent to 1. So this equation, a, the graph will start at a divided by 1 plus b. Okay. Now look what happens when t approaches 0. Again, the decaying exponential decays away to 0. We're left with a over 1, so the function a of t approaches the value of the constant in the numerator. Here's a graph of the logistics equation with some numbers substituted. For a, I used 10. And you can see that right here. As t increases towards infinity, the logistic curve asymptotically approaches the line a equals 10. Okay. In the numerator, we have the decaying exponential that gives rise to this nice smooth approach to a equals 10. What is the value at 0? E at 0 is 1, so 10 divided by 2 is 5, and you see that it starts off right here at 5. Now if t is less than 0, then the exponential is growing. Well, if an exponential gets bigger and bigger, that means the denominator here gets bigger and bigger. That drives the whole equation to 0, the whole fraction to 0, and you see that out here the exponential, or the logarithmic function, is approaching 0. Here is a plot of actual data for the growth of a population of yeast. You can see on it this sigmoid shape of the logistics curve. So there's a lot more utility for these equations of limited growth in the quote-unquote real world than there is for that unlimited, unbounded exponential growth. So we have two equations of limited growth. One is a creep function, and the other is a logistics function. You'll also see the creep function in electrical engineering when you look at the charging up of a capacitor, for example. I'm going to talk about logarithms now. A logarithm is a function with a long name. When we first start talking about functions, we name them with single letters like f of x or g of t or h of x. And that was very convenient for most of math notation. If I write two variables next to each other like x, y, what I mean is x times y. So when you write log or ln, do you mean l times o times g? No, that is the name of the function. This is for historical reasons. It's called log. It is still called log today. And then, of course, the natural logs are called ln. It makes the notation a little bit cumbersome. Even the values of logarithms are hard to compute because the logarithm is an inverse of the exponential function of the equivalent base. So to create that inverse function, you could look at your logarithm, that increasing, say that growth curve, draw the line x equal y, and reflect the the curve about the line x equal y, and you will draw the curve for the logarithm. But there are no nice, easy algebraic ways to determine the value of that logarithm. Just like e did not have a very easy way to compute it, neither does logarithm have an easy way to compute it. And I've given you one series expansion here. Of course, this goes on forever, and it doesn't look like the easiest thing to compute anyway. How does a calculator determine logarithms? Well, it can use a lookup table and interpolate between the values of the lookup table to give you your value of your logarithm. In the old days, there were these big tables, and there was these books like CRC manuals, and they contained many, many pages of paper, and the paper appeared to be even thinner than the ink that was printed on it, and this listed page after page of logarithmic values. Now, of course, they're all stored in your calculator, and all you have to do is punch in the number, but it's essentially the same thing. There is no quick, easy algebraic way to compute the value of each logarithm. I'm going to show you here how the logarithm is the inverse of exponentiation. You can try this on your calculator. If you take the log of some number like 9876, you get an answer. In this case, 3.99458. That goes on. If you let that answer become the exponent of 10, and I chose 10 because log without a base specified is log to the base 10. So I take the equivalent base, raise it to the power of the answer, I will get back the original value that I took the logarithm of. 10 to the x was the inverse of log. It works the other way too, of course. If I take, for example, e to the 1, 2, 3, 4, I get this tremendously large number, 5.3058 times 10 to the 535th power. If I put that answer in as the argument of log, then I will get back the original number that was the exponent of e. Log is the inverse of exponent. Exponent is the inverse of log. Remember that log is a function. Everything that comes after it really should be in parentheses, and it is called the argument of the function. Just like f of x, now you have ln, and in this case 8.3059 times 10 to the 535th. With functions, the inverse operation is that of composition. Okay? But if I tried to write these as composition, it gets incredibly awkward. I'd have to take ln composed using that open circle with e raised to the something evaluated at x. That would give me the log of e to the x. Because they're inverses, you get the x back. If you started with the exponent, 10 raised to some power, and you composed it with log, evaluated it at x, it would look like this, 10 raised to the log x. The answer is the x back because the exponent is the inverse of the logarithm. This is very awkward notation. It's generally not used, but we get sloppy. We write ln, and then we write e to the x after it, or 10 to the x after it, and we forget that what we're really working with are inverses. We're really working with a composition of functions. Here's a plot of the logarithmic curves. While exponential growth is very fast, logarithmic growth is very, very slow. Notice that all the logarithms, all the curves of all these logarithms go through the point x equals 1, y equals 0. If you remember, the exponential curves all went through the point x equals 0, y equals 1. But when you reflect something about the line x equals y, when you reflect it about the diagonal line, what you do is switch the values of x and y. So for on the exponential curve, you had everything going through 0, 1. On the logarithmic curves, you have everything going through 1, 0. The slow growth, you can see here, and how long it takes it to get to the value of 1 in terms of y. If you take the log of a number that is equivalent, that is the same as its base, then the value is 1. So here's log, again that's base 10. When I take the log of 10, I get 1. It takes that long till x equals 10 until the y equals 1 on the logarithmic curve for log. ln, of course, reaches 1 a lot sooner because its base is e, which is 2.71828, and so you see that point right here. Notice that all the logarithms approach a vertical asymptote of, that's x equals 0. This is a vertical asymptote of x equals 0. For inverse functions, vertical and horizontal asymptotes are exchanged. For the growing exponential function, you had a horizontal asymptote of y equals 0. For the logarithmic curve, which is its reflection, then you have a vertical asymptote of x equals 0. Many physical processes are logarithmic. One is the pH scale, where pH is the negative of the log of the hydrogen ion concentration. That's used a lot in chemistry, of course. The Richter scale, which we're familiar with here in Alaska, is the log of the amplitude of the wave of the earthquake in microns divided by the period of the earthquake, and that's t, in seconds. There are some correction factors here that are sometimes added in, but the Richter scale has, over time, actually been a very good scale for logarithms, or for earthquakes. Again, it's a logarithmic scale, and the pH is another example of a logarithmic scale that's used in science. Hearing is also logarithmic, and that led to the decibel scale. It is applied in electrical engineering to amplifiers for acoustics, such as speakers, but it's also used for any amplifier. And the decibel scale is written in two ways. You'll see it written for voltage. If you look at the voltage signal that's into the amplifier and that comes out of the amplifier, if you look at that ratio, you must multiply the log by 20. If you look at the power in and the power out, then you multiply the log, the answer there, by 10. I'm now going to use the laws of logarithms to go from the power law to the voltage law. So here we have the one of the laws of logarithms, that the log of any base raised to an exponent, I'll say n, can be written with the n out in front, n times the log of x, and we'll use that. I'm going to start with the dB power law of 10 log p out over pn, p out being the power that comes out of the amplifier, pn is the power in the signal that's going in. Then I have to use the equation that connects power with voltage. If you don't know electrical engineering, you don't need to. You can still appreciate this derivation without even knowing what this means. So you start with a law, 10 log p out over pn, and then you have an equation, p equals v squared over r. So I start here with my power law. Then I write power in terms of voltage. Here. Okay. Remember, everything after the log is really in parentheses. So we can use PEMDAS to evaluate it. PEMDAS, if you aren't familiar with that, is parentheses, exponents, multiplication, addition, parentheses, exponents, multiplication, division, addition, and subtraction. It's the order of operations. All right. Well, if the resistance is the same throughout the circuit, I can cancel those resistances and end up with the ratio of the output power squared over the input power squared. Right. I can move that the square, the power 2, outside of both of those terms, and now make use of the law of logarithms that the 2 can come out in front. Now remember, when the 2 comes out in front in logarithms, it multiplies any numbers that are out there. So the 2 multiplies the 10. And now there's my log, there's my dB law for voltage. And that is why there's a 20 in front of it, while there's a 10 in front of power. The reason is that power goes as the voltage squared. In the homework, there's a question on computing the pH. I'm going to go through something similar in logarithms so you can see how it's done. Say you only knew the log of 2 and the log of 3 and the rules of logarithms. You can use these to your advantage to actually take very complicated numbers, and if you can reduce them to powers of 2's and 3's by using the law and then use the law of logarithms, you can compute quite a few numbers, even independent of your calculator. This is just a good demonstration of the rules of logarithms, and it also stresses the importance of being very consistent in your calculations. Okay, we're going to start with the dB gain for a voltage amplifier, which is 20 times the log of V out over V in. The input voltage is going to be 3 millivolts. this is engineering notation. Milli in engineering notation is times 10 to the minus 3. So I'm going to write both of them in terms of voltage. Here's the output voltage will be 18 kilovolts, so it's 18 times 10 to the third. So they're both in volts. I can make this ratio out of them right here. Okay, I've seen people have a little trouble with such numbers. Right? 18 times 10 to the third is a monomial. 2 times 10 to the minus 3 is a monomial. It could just as easily have been 18 times x to the third over 2 times x to the minus 3. That x sitting there means times, of course. It is not another variable. But it's you can't write the 10 right next to the 18, or it wouldn't be clear what you were talking about. So because it's a monomial, I can take those coefficients, those numbers, 18 over 2, and just divide them and get a 9. Then the terms with the exponent is 10 to the third over 10 to the minus 3. The bases are the same. It could just as well have been x's or y's. Y to the third over y to the minus 3, you would know what to do. You would subtract the exponents, and 3 minus a negative 3 is 6. In this case, the base is 10, and we end up with 10 times 10 to the 6th. It's very important that you can calculate numbers like this. It would be very, very bad if you wrote out all the zeros and then tried to make the division like a long division problem with a whole bunch of zeros and some decimal points in it. It would be very error prone, and that's not the way to do it. You just make use of this exponential notation. So I took 18 over 2 and got the 9. I looked at the 10, and I got 10 to the third over 10 to the minus 3. I subtracted the exponents, and I got 10 to the 6th. Okay. Remember, 9 times 10 to the 6th is totally in the argument of log. Okay. All I'm doing is working out the inside of some parentheses as though I was working in PEMDAS. If I want to break that log out into two pieces, I can do it. Remember, if two terms are multiplied together like they are here, I can break those out as a sum of two logs. The log of x times y equals the log of x plus the log of y. Where does the 20 go in all this? The 20 is multiplying the log. It has to sit outside. Okay. So I keep the 20 on the outside. I put my expansion of log on the inside. And I wrote 9 as 3 squared. Obviously, we can use the law of logarithms and put that 2 out in front. Then we have the log of 3 plus 6. Right? 20 is still on the outside. I can substitute for the log of 3, and there I have the answer. You can work that out. So in this lecture, the important things to take away are those equations of limited growth. I'm sure that you already know quite a bit about exponents, and you might know a certain amount about logs. But those equations of limited growth are the ones you're going to use in your application when you go out into economics, biology, electrical engineering, mechanical engineering, any field that you're going to go study from here. You'll use equations of limited growth because they reflect reality. And in calculus as well, this semester and next semester, you will use both of those equations. I'm going to show them to you one more time. Here was the first one that I was calling the creep equation. It has a value out front. In this case, it's 1. That's the value that this function will approach as time goes to infinity. Because you have that decaying exponential inside the parentheses, subtracted from 1, it starts at 0. And this is a very common equation. Take a look at it and get familiar with it. The other one is a logistics equation. So here's a logistics equation. Again, you have a fraction, and in the denominator you have the decaying exponential. You end up with this sigmoid sort of curve, and you have to evaluate it. Always evaluate these functions when t equals 0 and see where they start. Then look at their behavior as t goes towards infinity. The decaying exponential gives a very smooth curve, very smooth rise to this logarithmic function and also to the creep function. For the exponentials, the point is that you have to be very careful in your calculation of exponentials. In the past, before there were calculators and people had slide rules, you learned very well to be careful about these exponentials because you're looking them up in tables, you're using your slide rule, and it just sort of trains you that way. Now we use the calculators and we sometimes get a little sloppy with certain things. Calculators are wonderful, letting us do many problems that we couldn't do before, but we do have to remember how to do these calculations. Use parentheses. Anytime you have a doubt, use parentheses. They are very cheap. There's no problem with using parentheses. You can use as many as you want. Don't trust the order of operations on a calculator. Don't really trust them in a computer either. And don't trust yourself with them. If you want something done as a group, put parentheses around it. And the arguments of all functions actually should be in parentheses. Right. Log is just a function with a long name. So those are the two big ideas to get away from this, to take away from this lecture: equations of limited growth, and a lot of care and diligence in performing logarithmic calculations.